Muy buenas tardes, sean todos bienvenidos al acto inaugural del 34º Simposio Internacional de Estadística, Inteligencia Artificial. Es un privilegio contar con su valiosa presencia. Este espacio, el espacio que genera este 34º Simposio Internacional de Estadística, Inteligencia Artificial, es, sin lugar a dudas, un espacio que a lo largo de los años se ha consolidado como ese punto de encuentro fundamental para el intercambio académico, científico y profesional entre quienes dedicamos nuestra labor a comprender y transformar el mundo a través de los datos. Este año, 2025, nuestro simposio se enmarca en un contexto particularmente relevante: la confluencia entre la estadística y la inteligencia artificial, un cruce de caminos que no solo está redefiniendo el futuro de la ciencia, sino también nuestra forma de interpretar la realidad, de tomar decisiones informadas y de enfrentar los desafíos más complejos de nuestra sociedad. El objetivo que hoy, en este 34º Simposio Internacional de Estadística, nos convoca es ambicioso y profundamente estimulante: promover el diálogo, la reflexión y la colaboración en torno a los avances, aplicaciones y retos actuales de la estadística en el contexto de la inteligencia artificial, integrando en este simposio esos enfoques innovadores en campos tan dinámicos como el Big Data, la ciencia de datos, la bioestadística, el Machine Learning, entre otros. Me permito entonces dar la bienvenida muy cordial y agradecer su valiosa presencia a quienes conforman la mesa de honor. El saludo y el agradecimiento a la rectora de la Universidad de Nariño, la doctora Marta Sofía González Insuasti. Está también haciendo parte de esta mesa de honor, y gracias por su valiosa presencia, el vicedecano de la Facultad de Ciencias de la Universidad Nacional de Colombia, el doctor Freddy Ochoa. Está también con nosotros el doctor Mario García Molina, director del área curricular de Economía y Desarrollo de la Facultad de Ciencias Económicas de la Universidad Nacional de Colombia. Está con nosotros el doctor Hernán Abdón García, director del Centro de Estudios y Asesoría en Estadística, CEACE, de la Universidad de Nariño. La doctora Gelis Mestre Carrillo, directora de Ciencias de Datos de la Universidad de La Salle. El doctor Ramón Giraldo Henao, director del Departamento de Estadística de la Universidad Nacional de Colombia, sede Bogotá. La doctora Lidia Rubiela Fonseca Gómez, cofundadora STEAM. El doctor José Alfredo Jiménez Moscoso, coordinador del 34º Simposio Internacional de Estadística 2025. Agradezco de verdad la presencia de todos ustedes, investigadores, docentes, estudiantes y profesionales que nos acompañan desde distintas regiones y distintos países. Su participación de verdad enriquece enormemente este encuentro y nos inspira a seguir construyendo una comunidad sólida, interdisciplinaria y comprometida con la excelencia académica. Por favor, de manera respetuosa les pido nos pongamos de pie y vamos a entonar orgullosos las notas marciales de dos himnos. Las notas marciales del himno de nuestra amada República de Colombia y el himno de la Universidad de Nariño.
Oh, gloria in excelsis en quietud por las sombras escrota, el humilde desgasta un laurel.
Semillero de amor y de lumbre, junto al libro, la mies y el hoz, otro sol amanece en tu cumbre, juventud, juventud, juventud. Y embriagados del místico vino que suscita invencible poder, esculpieron tu lema divino, dando vales con nuestro saber. Semillero de amor y de lumbre, junto al libro, la mies y el hoz, otro sol amanece en tu cumbre, juventud, juventud, juventud.
34º Simposio Internacional de Estadística, Inteligencia Artificial. Saludo también a nuestros seguidores a través de las redes sociales y nuestros televidentes. Facebook, Universidad de Nariño. Facebook, Telepasto Online. Estamos por YouTube. El link es Telepasto. Estamos también por la señal abierta de Telepasto. Un saludo también al comité organizador de este Simposio Internacional de Estadística y el agradecimiento. José Alfredo Jiménez Moscoso, Rubén Darío Guevara González, Ramón Giraldo Henao, Hernán Abdón García, Lidia Rubiela Fonseca Gómez, Yelis Igret Mestre Carrillo, César Andrés Palacios Abril. El comité organizador de este Simposio Internacional de Estadística. A continuación, por favor, las palabras de la rectora de la Universidad de Nariño, la doctora Marta Sofía González Insuasti.
Muy buenas tardes para todos y para todas. Un saludo cordial de bienvenida a este espacio académico, este espacio de encuentro, de discusión y de interacción en el Auditorio Luis Santander Benavides de nuestra querida Universidad de Nariño. Mi saludo respetuoso a quienes me acompañan en la mesa de honor, a nuestros invitados ilustres de diferentes universidades del país, a nuestro líder en la organización aquí internamente en la Universidad de Nariño, el profesor Hernán Abdón García, y a todo el equipo de nuevos amigos y colaboradores que formaron parte del comité organizador de este evento. Igualmente mi saludo al señor decano de la Facultad de Ciencias Exactas y Naturales, el profesor Hernán Escobar, a los docentes y las docentes de nuestra universidad, de las diferentes instituciones que hoy nos acompañan, a los invitados especiales y por supuesto mi reconocimiento y mi agrado por tener aquí a muchos estudiantes y muchas estudiantes de diferentes universidades del país y de otras regiones de Latinoamérica. Mi cordial bienvenida a este 34º Simposio Internacional de Estadística, hoy enfocado en un área de gran impacto, de mucha importancia como es la inteligencia artificial, un tema del cual no podemos alejarnos, un tema que nos une en este momento como humanidad y que nos pone un reto muy importante, aprender nuevas estrategias de enseñanza, de aprendizaje y sobre todo unirnos a la innovación, la ciencia y la tecnología. Y qué bueno que lo hagamos desde el ámbito de la estadística como una de las áreas más importantes a nivel de todas las ciencias, a nivel de todas las áreas del conocimiento, porque nos permite conocer de primera mano los datos, nos permite analizar y nos permite, por supuesto, tomar decisiones a futuro a raíz de estos resultados que obtenemos y que analizamos de manera muy juiciosa con el apoyo de quienes tienen la experiencia en el área de la estadística. Hoy sabemos que hay mucho por hacer, mucho por aprender y considero que aquí en nuestra universidad esta es una gran oportunidad para poder integrarnos, para poder conocer experiencias de otras universidades y empezar a estrechar esos lazos de unión, esos lazos de fraternidad académica y poder pensar también en el intercambio de nuestros docentes y estudiantes interesados en el área de la estadística. Yo quiero agradecer a quienes han hecho todo lo posible porque hoy estemos aquí. Desde hace ya varios meses tuvimos una primera reunión en la cual se nos motivó como Universidad de Nariño para poder hacer este evento aquí en la universidad. El profesor Hernán García, conjuntamente con el decano, nos plantearon la idea de poner a la Universidad de Nariño como sede y en ese momento les dimos el sí, porque queríamos que nuestros estudiantes tengan la oportunidad de conocer esta región, que los docentes puedan llegar aquí también y mirar a esta universidad, la única universidad pública y acreditada en alta calidad con origen aquí, en el departamento de Nariño hace ya 121 años y que hoy los recibe con las puertas abiertas, no solamente en esta ocasión, sino que los dejamos también como invitados predilectos para futuras ocasiones. Y posteriormente tuvimos también una reunión con el comité organizador, nos pusimos de acuerdo y hoy veo que esto ha sido un éxito, que faltan más personas por llegar aquí, pero que ha habido una afluencia bastante interesante y que se han podido conocer y que han podido desarrollar actividades académicas a través de talleres, a través de seminarios específicos y en este momento seguramente a través de esas conferencias magistrales con invitados de alto impacto que nos van a permitir conocer nuevos campos de la estadística y nos van a permitir integrarnos como universidades. Lastimosamente no puedo continuar acompañándolos en esta tarde por razones de agenda, pero los dejo aquí, en su casa. Estamos aquí para su servicio, esperamos que su estadía en la Universidad de Nariño sea muy fructífera y queremos que de aquí, de este simposio, no solamente salgan retos académicos y nuevos compromisos, sino también alianzas importantes a nivel académico nacional, a nivel académico internacional y que en el próximo simposio volvamos a encontrarnos con nuevas alternativas y siempre unidos por un solo propósito, el conocimiento en el área de la estadística. Bienvenidos, bienvenidas a esta su casa, la Universidad de Nariño.
Escuchábamos entonces las palabras de la rectora de la Universidad de Nariño, la doctora Marta Sofía González Insuasti. Nos decía ella que durante estos días, sin lugar a dudas, exploraremos juntos nuevas metodologías y compartiremos investigaciones y fortaleceremos redes de cooperación, que sin duda enriquecerán nuestro trabajo y nuestra comunidad científica. Vamos a recibir ahora el saludo de la decana de la Facultad de Ciencias de la Universidad Nacional de Colombia, sede Bogotá, la doctora Lucy Gabriela Delgado.
Muy buenos días a todas y a todos. En nombre de la Facultad de Ciencias de la Universidad Nacional de Colombia me permito darles la más calurosa bienvenida al 34º Simposio Internacional de Estadística, que este año tiene como eje central la inteligencia artificial. Quiero felicitar y hacer un reconocimiento especial a todos los integrantes del Departamento de Estadística, sus estudiantes, el personal administrativo, los egresados, pero especialmente al cuerpo docente. Son mis colegas quienes con su excelencia académica y proyección científica hacen de este simposio un espacio de enorme valor y trascendencia académica. Como facultad respaldamos esta iniciativa que promueve el diálogo interdisciplinario, la investigación colaborativa y la formación de avanzada en un área tan importante y significativa para el desarrollo del conocimiento mundial. Este año El simposio tiene lugar en la hermosa ciudad de Pasto, con una agenda donde se articulan los temas de estadística con los desarrollos más recientes en inteligencia artificial, que van desde la ética a la regulación de algoritmos, pasando por el aprendizaje profundo y el modelado probabilístico. Estas temáticas no solo son importantes, sino también urgentes desde su dimensión social, científica y académica. La participación de expertos nacionales e internacionales enriquece no solo la academia, sino todos los intercambios científicos necesarios para nuevas colaboraciones y nuevos aprendizajes. Esta enorme diversidad, tanto de expertos, investigadores, docentes y estudiantes, pone a Colombia en el panorama científico internacional con una enorme relevancia. Desde la Facultad de Ciencias de la Universidad Nacional de Colombia, reafirmamos nuestro compromiso con el avance del conocimiento, con la generación de nuevo conocimiento, con la formación de nuevos profesionales que integren el rigor de la estadística con la innovación tecnológica y con un alto compromiso social. Les deseo que sea un simposio muy exitoso. Bienvenidas y bienvenidos.
El saludo entonces de la decana de la Facultad de Ciencias de la Universidad Nacional de Colombia, sede Bogotá, la doctora Lucy Gabriela Delgado, y nos informaba que en este espacio el propósito es claro: promover ese intercambio académico y profesional en torno a los avances y los desafíos actuales de la estadística en el contexto de la inteligencia artificial y disciplinas afines. Y hablando precisamente de lo que convoca en este simposio, qué bueno que tengamos invitados especiales en este Simposio Internacional de Estadística en su versión número 34. Están con nosotros Shari Messenger, Francisco Gómez, Cristian Cabrera Jojoa, Juan Carlos Caicedo, Rodrigo Salas, Violeta Belber, Carl Henrik Eck y Sara Frati. Ellos son los invitados a este Simposio Internacional de Estadística. A continuación, las palabras del vicedecano académico de la Facultad de Ciencias de la Universidad Nacional de Colombia, el doctor Freddy Ochoa.
Gracias. Muchas gracias. Miembros de la mesa de honor, miembros organizadores de este evento, profesoras, profesores, investigadoras, investigadores, estudiantes. Es para mí un honor, en representación de las autoridades de la Facultad de Ciencias de la sede de Bogotá de la Universidad Nacional de Colombia, participar en esta sesión inaugural del 34 Simposio Internacional de Estadística, evento donde se divulgan los últimos avances en el campo de la estadística y que para esta ocasión nos traerá como temática central a la inteligencia artificial, el aprendizaje de máquinas, sus aplicaciones en ciencias de la salud e implicaciones éticas, campo que se remonta a los trabajos pioneros de Vannevar Bush, Alan Turing y John McCarthy a mediados del siglo XX y que ha logrado avances sin precedentes durante los últimos 70 años. Y hoy hemos tenido la gran fortuna de ver cómo esas ideas evolucionaron, avanzaron y llegaron a tal punto que ya no hablamos de inteligencia artificial y aprendizaje de máquinas como una posibilidad teórica, sino como una herramienta aplicada y práctica al servicio de la ciencia, la innovación y la sociedad en general. Hoy en día reconocemos el impacto que antiguas tecnologías de la computación ha tenido en la humanidad, como la máquina de diferencias de Charles Babbage en el siglo XIX, el ordenador electromecánico Mark I en 1944 o el ordenador ENIAC construido en 1947, considerado como la primera computadora totalmente electrónica, así como las ideas originales de von Neumann sobre lenguajes de programación, entre muchos otros desarrollos que aumentaron de manera vertiginosa la capacidad de procesamiento de datos. También vemos cómo nuevos desarrollos emergen, donde la IA permea en una enorme variedad de aplicaciones, en el procesamiento de imágenes y de lenguaje natural, en sistemas multiagente, en planeación y toma de decisiones, en el diagnóstico médico, en seguridad cibernética, en movilidad automática, entre muchos otros. Pero también vemos retos futuros en el uso de esta herramienta, no solo desde el punto de vista técnico, sino desde lo social y lo ético. En el papel que juega y jugará en la sociedad y en su accesibilidad y su alcance. Verla no como un reemplazo del pensamiento humano, sino como un medio que expande y enriquezca el conocimiento. Es así que en este evento se plantea como un escenario de intercambio transdisciplinar, donde tendrán la oportunidad de entablar diálogos y compartir ideas entre diferentes experticias como el área de la salud, la ciencia de datos, la ingeniería, la ética, el derecho internacional, entre otros. También tendrán la oportunidad de reflexionar sobre los desafíos futuros en términos éticos y científicos, en el uso de los datos y la inteligencia artificial. Pero también podrán escuchar charlas de nuestros ilustres invitados, a quienes les doy la más calurosa bienvenida. A la doctora Chari Messenger, profesora del Departamento de Ciencias de la Salud Pública de la Escuela Miller de Medicina en Miami. Doctora Chari, bienvenida. Al doctor Juan Carlos Caicedo, investigador del Instituto Morgridge y profesor del Instituto de Ciencias de Datos de la Universidad de Wisconsin en Estados Unidos. Doctor Juan Carlos, bienvenido. Al doctor Karl-Henrik Eck, profesor de la Universidad de Cambridge y codirector del programa doctoral en el Centro de IA-UCRI en toma de decisiones para sistemas complejos. Doctor Karl, bienvenido. A la abogada Sari Frati, coordinadora de alianzas estratégicas de la Organización Iniciativa Latinoamericana por los Datos Abiertos. Abogada Sara, bienvenida. Al doctor Rodrigo Salas, profesor titular de la Escuela de Ingeniería en Ciencias Biomédicas de la Universidad de Valparaíso en Chile y director del Centro Interdisciplinario de Investigación Biomédica e Ingeniería para la Salud. Doctor Rodrigo, bienvenido. Al doctor Cristian Cabrera, investigador asociado en el Departamento de Ciencia y Tecnología de Computación de la Universidad de Cambridge. Doctor Cristian, bienvenido. A la licenciada Violet Belver, coordinadora de Comunicación y Comunidad de la Organización de Iniciativas Latinoamericanas por los Datos Abiertos. Licenciada Violeta, bienvenida. Al doctor Wilmer Pineda, profesor de la Facultad de Estadística de la Universidad de Santo Tomás en Bogotá. Doctor Wilmer, bienvenido. Al ingeniero Edwin Fernando González, consultor y profesor de la Fundación Universitaria de los Libertadores en Bogotá. Ingeniero Edwin, bienvenido. Finalmente, es un placer para mí presentar al doctor Francisco Gómez, profesor del Departamento de Matemáticas, y al doctor Leonardo Trujillo, del Departamento de Estadística de nuestra facultad en la Universidad Nacional de Colombia. Doctor Francisco, doctor Leonardo, bienvenidos. No quiero terminar sin también dar la bienvenida a todas y todos los profesores, investigadores y profesionales ponentes de este extraordinario evento. Así pues, espero que encuentren en este simposio un escenario de aprendizaje e inspiración como estudiantes en formación o como científicos en sus proyectos de investigación o como ingenieros e innovadores en sus áreas de experticia. Y no me queda más que desearles muchos éxitos y que tengan unas discusiones enriquecedoras en los días por venir. Muchas gracias y que tengan una buena tarde.
El agradecimiento para usted, doctor Freddy Ochoa. Él es el vicedecano académico de la Facultad de Ciencias de la Universidad Nacional de Colombia, sede Bogotá. Y en sus palabras, el doctor Freddy mencionaba que es importante en este simposio explorar esas sinergias entre estadística e inteligencia artificial y su impacto en diversas disciplinas. También dialogó sobre esas posibilidades de compartir investigaciones, experiencias y buenas prácticas en áreas como la econometría, la biometría y la bioestadística. Y precisamente en estas áreas nos visita, y es un invitado especial, y lo queremos saludar también, al doctor Mario García Molina. Él es el director del área curricular de Economía y Desarrollo, en representación de la decana de la Facultad de Ciencias Económicas de la Universidad Nacional de Colombia, sede Bogotá. Le damos entonces la bienvenida al doctor Mario García Molina.
Bueno, miembros de la mesa y participantes en el simposio, en representación de la decana de la Facultad de Ciencias Económicas de la Universidad Nacional de Bogotá, la profesora Liliana Chicaiza, les doy un saludo muy especial. Ella no pudo asistir, pero me envió en representación de ella. Y para nosotros es muy importante el simposio, porque la relación entre economía, ciencias económicas y estadística es clave. no solo por el uso que hacemos todos los días de las estadísticas, la cercanía con el DANE, sino también porque hay una fertilización cruzada en las nociones y en los conceptos que se usan. Baste dar un ejemplo. Pensemos en el Premio Nobel de Economía que se le dio a Clive Granger y a Christopher Sims por la noción de causalidad de Granger. Era una noción estadística que arrancaba de una pregunta propia de economía y se plasmaba en series de tiempo. Entonces, esa relación ha sido estrecha, continúa, pero además de esas relaciones puramente académicas o intelectuales, hay algo que hace que este evento sea especial para mí personalmente. Al comienzo de mi carrera yo recuerdo con cariño uno de los primeros simposios, que en esa época era sobre series de tiempo, que fue de las primeras, de los primeros eventos de este tipo que yo estuve al inicio de mi carrera profesional. Pero además es muy grato ver que en este evento tenemos estudiantes de Economía de la Facultad de Ciencias Económicas, tanto del pregrado como de la maestría, que están como asistentes o como ponentes, y eso muestra una cosa, y es que el futuro para el evento, que se plasma tanto en que tenemos a los jóvenes que en el futuro son los que van a poder dar los avances a la disciplina, pero también en el hecho de que se está tomando como tema central la inteligencia artificial, que otra vez están planteando los problemas del presente y del futuro. Entonces, eso augura que nosotros no solo hemos tenido los 34 simposios hasta ahora, contando, sino que podemos esperar que tendremos mucho más simposios como este. Muchas gracias.
Gracias al doctor Mario García Molina, el director del área curricular de Economía y Desarrollo, en representación de la decana de la Facultad de Ciencias Económicas de la Universidad Nacional de Colombia, sede Bogotá. El invitado ahora es el doctor Ramón Giraldo Henao. Él es el director del Departamento de Estadística de la Universidad Nacional de Colombia, sede Bogotá. Doctor Ramón, bienvenido.
Bien, me complace profundamente darles la bienvenida al 34 Simposio Internacional de Estadística, organizado por el Departamento de Estadística de la Universidad Nacional de Colombia, con el invaluable apoyo de la Universidad de Nariño, de la Universidad La Salle y Stenco, a quienes agradecemos por acompañarnos en esta linda tarea y por acogernos en la hermosa ciudad de Pasto. Quiero expresar un agradecimiento muy especial a las autoridades académicas de la Universidad de Nariño, a su rectora, profesora Marta Sofía González, al director del CEACE, profesor Hernán García, también a los miembros directivos que nos acompañan en la mesa principal en esta tarde. Su respaldo fue fundamental para que este evento pudiera realizarse. Agradezco sinceramente a los miembros del comité organizador, quienes han trabajado con dedicación y entusiasmo para que hoy podamos encontrarnos aquí. Damos una calurosa bienvenida a los invitados nacionales e internacionales, muchos de los cuales han recorrido grandes distancias para compartir sus conocimientos con nosotros. A ustedes, colegas, estudiantes, investigadores y amantes de la estadística, gracias por su presencia y por su interés en construir colectivamente el presente y el futuro de nuestra amada disciplina. Nos acompañan conferencistas procedentes de universidades, centros de investigación y centros de investigación de gran prestigio, incluyendo las universidades de Miami, Cambridge, Wisconsin, Valparaíso, de la Iniciativa Latinoamericana para Datos Abiertos, ILDA, además de varias instituciones líderes en Colombia y América Latina. Este mosaico internacional de saberes enriquece nuestro simposio y fortalece los lazos de colaboración académica. Este año el tema central del evento es tan desafiante como fascinante: la inteligencia artificial. Vivimos una época donde los algoritmos no solo predicen lo que vamos a comprar, sino que escriben poesía, diagnostican enfermedades y hasta nos sugieren cómo redactar discursos, aunque aclaro que este lo preparé yo. En este contexto, la pregunta ya no es si la estadística y la inteligencia artificial deben dialogar, sino cómo y en qué lenguajes lo harán, porque si algo nos ha enseñado la historia de la ciencia es que las grandes revoluciones no ocurren en soledad, sino en el encuentro entre disciplinas. Hoy somos testigos de uno de estos encuentros, una alianza natural necesaria y me atrevería a decir felizmente inevitable. Un matrimonio feliz y próspero en el que no habrá divorcio. Un matrimonio como pocos hoy en día. Cabe mencionar que la tasa de divorcios ha aumentado a nivel mundial. Un matrimonio entre la rigurosidad estadística y la capacidad computacional y adaptativa de la IA. Esta unión ya está dando frutos en múltiples áreas. En medicina personalizada, donde la IA aprende de millones de datos y la estadística garantiza la validez de las inferencias. En la predicción del cambio climático, donde modelos estadísticos se combinan con redes neuronales profundas. En el análisis de imágenes y lenguaje natural, donde los datos fluyen, pero también deben ser comprendidos, interpretados y validados. En la educación, donde herramientas inteligentes adaptan la enseñanza a cada estudiante, pero donde la estadística nos permite medir su impacto real. Y por supuesto en la ética y gobernanza algorítmica, donde la estadística aporta transparencia, explicación y control a sistemas que, si bien potentes, también pueden ser opacos. El futuro de la IA en estadística no está solo en automatizar análisis, sino en ampliar nuestras capacidades de comprensión y descubrimiento. La IA no reemplazará al estadístico, pero sí lo convertirá en alguien aún más poderoso, más creativo, más capaz de encontrar patrones y respuestas en la complejidad del mundo. Por eso, este simposio también es una invitación a abrir la mente, a compartir el conocimiento y a imaginar nuevos horizontes de investigación colaborativa entre estadísticos, informáticos, ingenieros y profesionales de todas las disciplinas. Antes de concluir, quiero contarles con gran entusiasmo que el Simposio Internacional de Estadística del año 2026 se celebrará en la ciudad de Bogotá, con una temática que nos sigue retando intelectualmente, el análisis bayesiano. Desde ya quedan todos cordialmente invitados a seguir construyendo comunidad y conocimiento en torno a esta poderosa forma de pensar la incertidumbre. Una vez más, gracias a todas las personas que han hecho posible este encuentro, a la Universidad de Nariño por su generosa acogida, a las Facultades de Ciencias y Ciencias Económicas de la Universidad Nacional de Colombia, sede de Bogotá, a la Universidad La Salle, que será la sede del Simposio Internacional de Estadística 2026, a los conferencistas por su compromiso académico y a todos ustedes por creer en la ciencia como un camino para transformar la sociedad. Les deseo una estancia académica provechosa, llena de aprendizajes, debates y nuevos lazos de colaboración. Y también los invito a disfrutar de la cultura, la gastronomía y los paisajes de esta ciudad tan especial. Que este evento nos inspire a seguir trabajando juntos, estadística e inteligencia artificial de la mano, no para predecir el futuro, sino para construirlo. Muchas gracias.
El agradecimiento entonces al director del Departamento de Estadística de la Universidad Nacional de Colombia, sede Bogotá, el doctor Ramón Giraldo Henao, quien nos hizo una aclaración muy importante, que el discurso lo elaboró él, no la inteligencia artificial. Eso es importante tenerlo en cuenta, pero es valioso también saber que ahí podemos encontrar una gran fuente de información. Tengo una observación, una recomendación para todos los asistentes, es con relación a su escarapela digital, para que la tengan por favor siempre a la mano, al día, sobre todo por el pequeño inconveniente que se tuvo hoy en el horario del almuerzo, dada la ubicación de los buses que los transportaron hacia el Hotel Morasurco, para que por favor en el transcurso de estos días se optimice esa presentación de esa escarapela virtual y digital, y así poder agilizar ya el transporte de ustedes hacia el lugar donde van a tomar su almuerzo. Muy bien, con gusto, por favor, vamos a presentar la conferencia inaugural de este 34º Simposio Internacional de Estadística de Inteligencia Artificial. Le agradecemos, por favor, a la mesa de honor su participación para que, por favor, tengamos el lugar adecuado para esta conferencia. Muy bien, el doctor Hernán Abdón García, con una información.
Muy buenas tardes para todos. Sean bienvenidos a este Simposio Internacional de Estadística. Simplemente para darles una información. Las personas que van a trabajar con pósters, pues aquí hay una parte donde sacan la fotocopia, pero es bueno que lo lleven a la Facultad de Artes. La Facultad de Artes es al frente, ¿sí? Ahí lo llevan y con el señor Yaqueno, él se encarga de recibirles, porque la sesión de póster va a ser el jueves en la tarde. Entonces, que por favor les lleven allá los pósters para que realmente podamos presentarlos el día jueves en la tarde. Muchas gracias.
Es grato entonces dar inicio a la conferencia inaugural del 34º Simposio Internacional de Estadística, Inteligencia Artificial. Es un honor de verdad presentar al doctor Karl-Henrik Eck, destacado investigador en el área de la inteligencia artificial y el aprendizaje automático. El doctor Karl-Henrik Eck actualmente se desempeña como académico de la Universidad de Cambridge y cuenta con una amplia trayectoria en investigación aplicada a la inferencia bayesiana, la representación de datos complejos y el aprendizaje profundo. El trabajo ha contribuido significativamente a la comprensión y desarrollo de enfoques probabilísticos para el aprendizaje automático, combinando de manera rigurosa la estadística bayesiana con modelos profundos, abriendo así nuevas posibilidades para la interpretación y la generalización de algoritmos inteligentes. Hoy está con nosotros aquí el docente investigador Karl-Henrik Eck, con su aprendizaje profundo bayesiano, en el que explorará los fundamentos Karl-Henrik Eck, y agradecemos profundamente su participación en este simposio, y es un privilegio, doctor, contar con su presencia. Para usted este aplauso y muchos éxitos.
Fantastic. It's a real pleasure to be here. Thank you so much for the invitation. And I only speak a very, very poquito bit of Spanish, but I could hear from Ramon's talk where he was saying AI and you all laughed. And I completely agree, right? And an event like this really shows us the science is about people, right? That's how we get stuff. That's how we learn things, right? And even if we could have AI, which we're never going to have, that's not the important thing, right? It's what we can understand about it. So my name is Karl-Henrik Eck, and I'm a professor in Cambridge and also at a medical hospital in Stockholm called Karolinska Institute, because a lot of the applications that I work on are related to medical and health. And the last bit of thing is Pembroke College in Cambridge, where I'm a fellow. So I thought I'll tell you a little bit about myself to begin with, and that's just all academic stuff, right? So I thought I'd tell you about the important things in life. So this here is my bike, right? For those of you who knows bikes, should be able to spot that this is a Colnago Master Extra Light. Columbus tubing.
Muy buenos días a todas y a todos. En nombre de la Facultad de Ciencias de la Universidad Nacional de Colombia me permito darles la más calurosa bienvenida.
She's absolutely beautiful. So now the thing is, that photo is taken in my hometown in Sweden. Beautiful, we've got mountains, not as good as the mountains here in Pasto. When I arrived here, I've only been thinking about my lack of a bike, right? You've got amazing places to ride. I don't live in a particularly amazing place. You can see London there. Cambridge is this tiny bit up there. There's a nice city there called Bristol, where it's usually my base. There's two really nice rides you can do. So you can do a northern ride, and you can go to this place called Port Talbot in Wales. Lots of nice hills crossing the bridge, and Port Talbot is a steel mill. And steel workers eat a lot, just like cyclists, so it's a very good place to go. Another ride you can do is you can go south, you can go into a national park called Exmoor, and one day I did this ride, and I ended up where that red thing is, and I was looking across the Bristol Channel, and I saw this. I took a photo. So then I looked at that photo, and I thought, oh, that's kind of cool. There's some buildings over there. And I realized that's probably the steel mill in Port Talbot. Interesting, I thought. So now I had a long ride to go home, right? So I was cycling home, and couldn't really get this image out of my head. So when I got home, I went to Google Maps, and I did a measurement. Turns out it's about 20-odd kilometers across the Bristol Bay. And then I put this into a calculator that calculates, the circumference of the Earth at that distance. And it turns out the distance to the horizon would be 6.2 kilometers if I'm standing up, taking a photo at this height. That means that the hidden height at the distance of 20 kilometers would be 125.6 meters, right? So then I went back to this photo, and I thought there's some big things here. You can see a chimney there. You can go onto a website called tallbuildings.org, and you can check how tall that is. It's a lot shorter than 125.6 meters. So now I had a bit of an existential crisis, right? I was thinking, how the hell can I see this thing? Until it all became clear to me, right? And you all see this now. I've been living a lie, right? Because the thing is, this whole notion of a spherical Earth must clearly be a lie, right? We live on this plane, and it perfectly explains this thing, right? I'm glad you laughed, because if you wouldn't have laughed, we would have had a slightly different problem than talking about statistics, maybe. So why is this, right? Why do we laugh about this thing? If you think about it, this thing, the explanation I just gave, that the Earth is flat, is a perfect explanation for that data, right? It supports that data. So now you can think of, okay, but we laugh about it and have another explanation. Well, what we usually do, right, is that we say, if I got multiple types of explanations, we would imply something called Occam's razor, right? To think about the notion that we should, given multiple explanations, we should pick the simplest one, right? So here I got two explanations. The Earth is flat, the water surface is flat, therefore I can see the building. Doesn't get much simpler as that, right? The other explanation would be this. Due to a temperature gradient between the water and the air, there's a dispersion of water molecules into the air proportional to the distance to the surface, effectively creating a lens allowing us to see around the bend of the Earth's curvature, right? If I apply Occam's razor to this, come up with a measure of complexity, you're always going to pick the first one, right? Agree? Right? Still, we don't like that, right? So, what I'm going to try with this notion, and it explains other things as well. Why did the dinosaurs disappear, right? Well, we had this disk floating in space, and then sometimes it just wobbled and all the dinosaurs fell off, right? Explains lots of things. So, This problem that we all laughed about is exactly the problem that we're trying to address in statistics and in machine learning. It's the thing that always comes biting us back. So let's simplify this problem. I've got a set of data points that lies on this half sine curve. And now what I want to do is I want to find an explanation so I can say something about other points, right? I want to be able to argue about other things where I don't have observations, right? In the same way, I want to be able to take the data of seeing these buildings, build some form of theory, and say something about something else. Now, the problem is, I can come up with a multitude of theories, here symbolized by a multitude of functions, that would be exactly the same on all these data points, but would be fundamentally different everywhere else, right? This is the problem that we're always tackling. What we can also actually say, which is, if I look at a specific line, so x equals to a half in this case, I can come up in the space of functions. There are functions that passes through exactly these data points that gives me any value. The intersection with the green line is any value between minus infinity and infinity, right? That's the problem, and this is the thing that we refer to as no free lunch, right? This is the no free lunch statement of machine learning, something we can never, ever get around. And this is the problem if you work with something that's quantitative. So, what is then machine learning, and what do we do in machine learning to think about this? I think about machine learning in this way. I think it contains three components. I got data, I got a model, and I take those two together through computation, allows me to do predictions. Now, in each of these elements here, I want to input assumptions, constraints, beliefs, these kind of things, because otherwise I can never ever trust my predictions. Just as in the case before, if I don't reduce the space of functions, if I don't reduce the space of functions to, for example, in this case, I really want a smooth explanation, so I'll reduce and remove all the other functions. Now I can do something. If I don't add these in, this comes biting us in the back, right? So, now, data, if I think about my model as one way of making assumptions, that's saying I only want smooth functions, for example, you can look at how data and model interacts. So I like to think about this in this type of Pareto front setting. And for those of you who already saw this morning, you hopefully know what I'm talking about. If I'm in a scenario where I've seen everything I'm ever going to see, right? You know every question that anyone is ever going to ask you. The world doesn't need machine learning. It needs a lookup table, right? If you're in the other end, where you got perfect truth, you know what the function is, you don't need any data. Right? This is how these things interplay with each other. Machine learning is the task that sits somewhere in the middle. I don't have enough constraints in terms of my model, I don't know everything, and I neither have enough data. So I want to balance these two together somehow. And that is what machine learning effectively is. So now, how do I input constraints? How do I input things that limit the modeling space that I have? Well, we do this through distributions. Distributions quantifies our beliefs in a specific value of a variable, right? So in this case here, I got x and I got density over it. It says how much I believe x to be a specific value. Now, what we would want to do then in the machine learning chain of things is that I want to say data, well, it follows some form of distribution. At least I have empirical data, so I have an empirical parameterization of this distribution. Then I want to parameterize my beliefs in terms of a model. And then I want to push this through to say something, what those beliefs say about my predictions, my beliefs over my predictions. So that implies I need to propagate uncertainty through some form of computation. The nice thing, we know how to do this. This fella, Reverend Bayes, showed us exactly how to do this, right? So we have mathematical means of propagating uncertainty. So That means the machine learning tasks or the questions that we need to address is the first one, modeling. How do we define our domain knowledge mathematically and place distributions of it? This is why I spend most of my time in my hospital position is just sitting talking to doctors. Doctors are absolutely amazing with what they do, but they don't have a formula for what they do, right? So my task is to try and extract as much experience from them as possible, try and write down the math for it, and try and mix that with data from every doctor there is, right? Now I can do a beneficial thing. Second thing is the inference task. How do I combine knowledge with data? This is often computationally very hard, so we need to spend a lot of time doing this. And then my final thing is then when I output predictions, how can they support decision making, right? I shouldn't make decisions, I'm a machine learner. These are to go back to a doctor who should be able to say, now I know what this means, I should do this, right? This is great. So the way I set this up, the field was kind of chugging along. We were biting off one bit after the other. And then something happened about 10 years ago, which I could only symbolizing by here was a bit of a revolution, right? Machine learning started doing things which we didn't expect it to do, right? We were predicting these small curves. I used to go to conferences having two-dimensional plots like that. And then all of a sudden, people started generating images and text and classifying, all sorts of things. What happened, right? Well, people came up or reinvented this thing called neural networks, right? Neural networks have lots of stories and narratives around them. This is how humans think. They're motivated by the brain. All sorts of things. Doesn't really function on me. I'm way too square and strange for that. So therefore, we're going to talk about these more in mathematical terms. But the real big thing that happened was that it turns out that these objects are really, really simple computationally. So we could scale them with enormous amounts of data. So what we did, if we go back to this plot, where I used to work with things down here. I had like 5 data points. And then I had to really, really work to come up with cool models that could still somehow break the no free lunch. Well, neural networks, they are like somewhere here. We have a super, super general function class that's completely unconstrained. And then, but because they're so computationally simple, we can use half the internet of data, right? And that means they're getting all their constraints from data. And this is great because you can do certain things like image classifiers and so forth where there exists lots of data. But it has 2 big problems. One, it doesn't predict with uncertainty. And secondly, we don't really know why they work. And thirdly, a lot of interesting problems I don't have big data. I generally even want to go as far as this. I don't think there's a single interesting problem that has big data. It might have large volumes of data, but that just means the problem is really hard, right? Images on the internet is not a good example of stuff you should actually work on, right? Cool. So let's then think what a neural network actually is. Let's just forget all the nonsense narrative and just think what it actually is. It's a composite function. It's a function through a function through a function through a function. Lots of them. Each function being very simple, okay? Why would I ever want to construct a model like that? Well, when I studied, the first thing I learned about composite functions was this, okay? So I've got the kernel and the image of the function. The image is basically all the values that the output takes, and the kernel is effectively all the values that map to the same value, right? Turns out, if you build a composite function, the kernel would only ever grow, and the image would ever always shrink. So what it effectively means, which is a bit counterintuitive, the deeper you make a model, the more layers you add, the less representational power you get, because more and more points will map to the same, and less, therefore, possible outputs exist. Simplest notion I have to think about this, if you take a piece of string, right? Now I have a function that's non-monotonic, turns itself, that means this point and this point map to the same value. Now I tie a knot with them. Now I push that to the same thing. You use tie knots, but you can never ever untie a knot, right? That's what happens. That seems like a really silly way of modeling stuff. So why does it work? Well, the problems that we attacked at first were things like take an image of dogs and take images of cats and classify them as dogs and cats. Well, now you want a function that takes an enormous amount of inputs but only gives two outputs, dog or cat, right? So it was exactly the type of functions that we wanted. The second thing that kind of appeared empirically, which I'm going to talk about a little bit now, is it turns out these models are super easy to learn. You just throw your gradient descent on it and it just works, right? So somehow what it says is that the energy landscape of these functions have some really, really desirable properties. And we know this empirically. And I'm going to try, I'm not very good with empirical analysis, so I'm going to try and show some math why that works. So then, as someone who comes from the probabilistic side of things, I just think, well, great, you've done these discoveries, now I'm going to improve them by just being Bayesian about them. So, super easy, I'm just going to specify priors on every layer, I'm going to integrate them out, and I'm going to win. I'm going to need less data, and I'm going to get uncertainties on the output. I was not the first one to think about this, and me or anyone else, no one succeeded. Basically, David Mackay, who was a very strong figure in the UK machine learning community, wrote in his PhD thesis a lot about this. Doesn't work. Empirically, the performance of Bayesian inference on composite function is just terrible. You're using an enormous amount of computational effort for basically no gain at all. It's not just parametric models. For those who will come to my talk tomorrow, I'm going to talk about non-parametric models as well. Still the same story. Doesn't work. So my question is then why? And that's what I'm going to try and talk a little bit about now. Try and get a hold of what makes these composite models hard to think about as statistical models? What is it that's just weird with them? So, the two papers that I'm going to talk about is a paper from last year from some of my students and colleagues called Reparameterization Invariance in Approximate Bayesian Inference, and then a paper which is in submission, but we got very good reviews, so hopefully it should be at NeurIPS this year, which is called Deep Variational Inference with Stochastic Projections. Great. So let's just think about doing statistical models of composite functions. So back to our function. I'm just going to call it F. It is this function where I got parameters W sitting on each layer. Okay? Now, parametric models are really weird. I struggle with parametric models myself. So, let's just take this line. This is a line with one parameter, right? You can only control the slope. What I've done is that I've uniformly drawn spaced values in parameter space. And then I've generated these lines. So this is my function space. Now this weird thing happens, right? Is that the distance between, the similarity between these two functions in parameter space are the same as the similarity between the two top ones, right? The two top ones, we would probably say, well, that's the same line. These two are definitely not the same line, right? So parameter spaces themselves has a geometry to them, okay? And we don't want to learn in parameter space. Parameters are just a means to an end, right? So we got this weird mismatch happening where we got a notion of similarity in our function space, and then we have a notion of similarity in our parameter space. Okay? So keep that in mind, and now I'm just going to try and do bog standard inference in this neural network. So Another thing you're going to keep in mind, I'm going to specify a really stupid prior on this. I'm going to come back to this at the end of the talk. So I'm just going to have a zero mean Gaussian, isotropic Gaussian on the parameters, and then I'm going to assume that I'm going to try and reach the posterior distribution over these weights. So the way we often do this, or the first way you would think of doing approximate inference in this case, is a Laplace approximation. So what we do here is that the integral in the denominator is the really tricky thing to compute because it propagates uncertainty, propagates a distribution through all these layers. So I'm just going to say that that's just the normalization factor. And then I'm going to find the maximum a posteriori estimate, W hat, of this thing here. Yeah? So then I got the mode of the posterior. And the Laplace approximation works like this. So I take the mode, take the objective function that I have, which is just the map, and I'm going to take that around the mode, and I'm going to do a Taylor expansion around the mode. So now the first derivative, because this is a maxima, goes away, and I only have this second derivative term. So it looks something like this. So I have the objective itself, and then I got a correction based on the Hessian of the loss function. So if I do this, I can simply plug this in to the approximation that I wrote up. Now you can see from this, I can just identify terms, and I can write this as a Gaussian. A Gaussian that has the covariance, which is the inverse of the Hessian of the loss function evaluated at the map estimate. For those of you who want a graphical explanation of this, this is effectively what we've done. So my true posterior would be this red curve. I found the maximum of this, and I fitted a Gaussian on the second order curvature of that. So I've just done a mode matching. So let's go back now to composite functions. So I'm going to take the simplest composite function I can think about. Really stupid function. It's a line, but now parameterize the line with two parameters, right? W1 times W2 times X, right? Thing with that is that there's a whole class of reparameterizations that I can do. If I scale W with alpha and downscale W2 with 1 over alpha, it's the same function. If you plot that in parameter space, you're going to see that all these parabolas are the same function, right? Okay? So now let's slap a Gaussian on that. Bonk. That's what we do, right? I put this Gaussian on this. Now I've done something very, very fundamentally wrong, right? So I put a Gaussian on this. All functions that are on a parabola, so let's focus on the yellow parabola, are the same function, right? I've slapped a Gaussian on it. That means a function here and a function there is the same function, but they have two different density values. So I've broken measure theory, right? So I've done something fundamentally flawed. The same object have two different densities, right? Doesn't work, right? If you now, what will effectively happen, if you apply the Laplace approximation, you can also see that the derivative, the curvature along this thing is completely flat, and then it just goes down one angle. So I'm going to fit a huge Gaussian on it. So that means this is not curated data. This is exactly how it looks like. Oh, sorry, you can't, the contrast's really bad. But I've effectively tried to fit that function, and I have samples all over this space. They're all over. Nothing goes through the data, right? Simply because it massively underfits this thing. Okay? So the problem is that I have a notion of similarity in the function space where I want to learn something which is different to the parameter space. So how do we get around this? Well, what I would want to do, right, is think about functions themselves, right? A similarity in function space, and embed this notion in the parameter space. Now I can work with parameters as well as I can work with functions. But how do you think about similarities in function space? Well, it's very, very hard, right? It's really hard to do. So I'm going to propose the simplest notion of similarity in function spaces I can think of. I'm going to say all these functions are the same under these 3 dots, right? So I'm going to give you a non-parametric notion where I say, if you have a set of data, all functions that are the same on those data points are the same function. They might be different anywhere else, but they are the same function on the data. So a little bit more formally, I'm going to refer to this as X reparameterizations. So given a data point, for any W, we define the reparameterization set such that the reparameterization set is all W's where they're equal on that point. And consistently, given a collection of points, we call the intersection of these X reparameterizations the capital X reparameterizations. Okay? So what I can do with this is I can define, or we have defined, a similarity notion over the parameter space RD, such that 2 parameters are similar if they are in this group. Now I can create the space of effective parameters, so just remove all the reparameterization by taking the quotient space of RD with that similarity measure. And now I get a set of parameters P, which are the true parameters. In the sense of the silly example with the line I had, they use this one, right? They're the diagonal. It's a one-dimensional thing, okay? So these 2 points are in P, are the same point if and only those 2 things are similar. So that's what this means. Now, I can continue with this completely algebraic version of working with this. It's a very useful construct, and it allows us in the papers to prove lots of things. But it's a completely useless concept computationally. It doesn't help me at all. So I'm going to now show you a slightly different route that hopefully will give you a bit of intuition for this. So what we would want is a distance in parameter space, so that if the distance between 2 sets of parameters is 0, it means that they're similar according to the similarity relationship we wrote up before. Now, what I can now do is I can take I'm going to do work on distance squared here to just remove a square root. I'm going to take the same point, and I'm going to perturb it a slight bit epsilon in parameter space. And I want that to be the same thing as if I perturb the function a tiny bit, right? So I want the notion of smoothness in the space of parameters to equate to the smoothness in terms of functions, where the right-hand side of this is exactly the X reparameterization that we wrote. Now, if I linearize the function around W, if I linearize around here, now I will get an expression looking like this. So I just take the point and then I have its gradient, right? The gradient, the change of this is the only thing that's going to invoke a change in this distance. First 2 terms cancel each other. And now I'm going to get something like this if I write this on matrix form. I'm going to get the distance that I perturb times the Jacobian of the function mapping from parameter space that realizes the function. Jacobian, and that again. So this here, you can think about, if you want to think geometry, which we're going to do now, is JTJ is a Riemannian metric in this case. It's called the pullback metric, for those of you who know differential geometry, that effectively says, if I move this much in parameter space, how much do I move here? And that geometry there now equates those 2 things. So it says, now, if I move according to this Riemannian geometry in parameter space, I'm now moving the same amount in function space. So we can now go back to the Laplace approximation, and we can put this linearization, so this similarity notion, onto here, right? So you know if you evaluate that Gaussian, you're going to have exactly that quadratic form, W times some covariance matrix inverse times W. Now I'm going to put a J there. J just transforms W. So now you do the Laplace approximation in the linearized space. This is known as the linearized Laplace approximation. There was a paper in 2021 that doesn't show where this comes from. I have no idea how they managed to try this, but they show this just works. Hopefully, I've given you a geometrical explanation why this works. This is also known as the Fisher-Rao metric. It is, very interestingly, not full rank. So it's a pseudometric. And hopefully you'll see why this is a pseudometric. So a pseudometric is something that has 0 eigenvalues. Oops, if we go back, we go back to here. The reason why it's a pseudometric is the distances completely collapse along these things. There are no distances along things that are reparameterizations. They're all the same, right? So if you move 100 miles along that thing, you're still in the same points. You haven't moved, right? In function space. Cool. So therefore, it has to have 0 eigenvalues. Great. So, just to hint at this, I have a proof to show that the pseudo-Riemannian manifold obtained by the pullback metric, the one we just described, is homeomorphic to the quotient group that we defined before. So the nice thing with this is that it allows us, we go on equivalence between the two. You can do lots of stuff in the algebraic space, and you can do lots of stuff in the geometry space. So that's quite a nice thing. If I now apply this, what you would have seen is that the samples go straight through this thing. Okay, and you get diversity outside. It's a little bit of a shame that we can't see these. So, now, if I would have a completely linear function, if I would actually have a linear function, then the derivative that I would take when I'm linearizing the function in the function space is the same everywhere, right? So now I've effectively taken the parameter space, I divided it up to an image of the GGN, so the actual eigenvalues that it has, that is where the function changes. And then I got the kernel, which is 1 minus that, so the eigenvectors in the directions where I have no eigenvalues, or the rest of the space, right, the null space. That is the kernel, and in that case, I can move as much as I want, I can reparameterize there, but I'm still getting the same function. Okay? So, the nice thing about having the linear thing is I can now perfectly split this space, and what I can do is I can show you something like this. If I just do the eigendecomposition of that matrix, the GGN that we had before, I'm going to have these two terms. And the really cool thing that I hope you can keep in mind is that alpha, here's my prior term. The rest comes from the data. So you've got one term here, which is the image. And this thing here is the kernel. This thing here has contributions from both data and prior. This thing here has no data in it. It's a term that the data can't decide, which is kind of nice, right? If you've got this parabola that looks like this, the data can tell me I should be on that parabola, but it can't choose the parameterization. The only information that can come from that is from prior assumptions, right? Great. Going to be a little bit quick on this. So now, in the linearized case, it's super easy. The GGN doesn't change. In the nonlinear case, what you would actually get is these smooth, they are smooth if the neural network is smooth, these smooth manifolds that looks like this. Okay, now I'm going to try and answer the first question I said. Why is neural networks so easy to learn? Well, look at that. You're trying to go down and find a point. What this thing does is that it takes that optimal point you have and it makes it a huge basin, right? It effectively creates these massive encatchment areas which all represent the same function, right? So if I'm now running gradient descent, the more layers I add, the bigger these things get. The kernel just grows, as we saw, right? The more layers I add, the kernel gets bigger and bigger. The number of reparameterizations just grows. So finding one of these just gets easier and easier, right? Do we get that notion? It's quite a simple one that I didn't think about until we actually did this, right? But that's really why gradient descent works so trivially in a neural network. And that's why we build composite functions. What I can also do, because I have the metric, is now I can propose a first way of sampling from this. So here, what I can do is that I can do a diffusion process, so basically define a random walk according to this metric. And now I can actually sample from this space completely. And if I do that, sorry, my images don't show very well, but if I do that, what you will see, ish, okay. What you will see is that if I sample from the kernel contribution, things that actually changes the function, I will get some variance. If I sample from the non-kernel contribution on the bottom line, I basically get no variance whatsoever. All those things are just reparameterizations of the same function. There's loads of functions there. They're written in completely different parameterizations, but they're all damn the same, right? Cool. So, taking stock, we've characterized the geometry of reparameterization that comes from compositions. The geometry explains why the linearized Laplace approximation works, because infinitesimally, it's invariant to reparameterizations. We derived a very simple random walk to sample from this manifold. Nothing fancy there at all. It's just Riemannian diffusion on this metric. So now, I wanted to hint at a slightly different thing. So when we did this, we could do inference over small models, right? Not big at all, right? A couple of thousand parameters, tens of thousands maybe, right? If I had more compute, maybe 100,000. So in terms of neural network land, tiny models, right? So what we then thought, let's write down a better approximation than the Laplace approximation. So what I'm going to try and do, and this is a bit of a weird one, there's situation marks and there's tildes and all these things because now I'm breaking mathematical notation. This is very sloppy. So I'm trying to say here, think about what machine learning actually does. It integrates a prior measure that has nothing to do with data with a likelihood measure that has everything to do with data to get a combined measure, P of y. And we always say that this is a great thing because it means I don't need to balance my constraints with my data fit term, right? This is the great thing about being Bayesian. You don't have a lambda, no regularizers and annoying things like that, right? Now, it's also slightly annoying because I got this combined measure that I have to work with. Now, what we've actually done, that I hinted at the previous slide, we've taken that measure that's been marginalized, and then we factorized it in two terms. I factorized it in one term, which is orthogonal to the data. The data has nothing to do with it, right? The image. And then I have something which has everything to do with the data, which was which one of these parabolas am I lying on, right? So in some sense, that puts us in a really nice space to propose an inference scheme that actually reflects that geometry. Something that can learn from data and something that cannot learn from data. So to do this, I'm going to have a very quick, how am I on time? Oh, fantastic. So I'm very good on time. 10 minutes, okay, yeah. I'll do 10. So, what I'm going to do is I'm now going to design a variational approximation to this. So I'm going to design a proposal distribution or a variational distribution that respects the geometry of the problem. So, for those of you who are not familiar with variational inference, I got one slide to show what variational inference is. So, I'm going to sit here now to point. The object that I'm interested in is P of y, okay? I get that by integrating out some distribution, pushing P of x through P of x given y, okay? Now that integral, for some reason, is computationally intractable. It definitely is for a neural network, right? Okay, so I can't do that integral. The other way to write this up is to write base rule in a funny way, right? So I put the posterior over x in the denominator, right? Now that's the same thing as this. So what I want to show with that is effectively getting P of y is effectively equivalent to having the posterior. If I have the posterior, I can just divide that term and I'll get P of y. So what we're going to do is that we're going to put a proposal distribution, Q of theta over x, which aims to approximate P of x given y. This proposal distribution is going to have a set of parameters theta. And we want these parameters theta to be sufficient statistics of x, of y, so that this thing does no longer depend on y. So effectively, if theta can encapsulate all the information that y has about x, well, now I can just drop x, which I've shown here by effectively dropping that arrow. There's no dependency between x and y. The way we can do this is that this is going to go a bit quick. I can write log p of y as is this. Okay, I chuck in the formula I had before in log, and then I write q of x in front of that. Because q of x is a distribution, it just integrates to 1, nothing happens, right? I've done nothing. I can expand this to 3 terms. Something that just depends on q, something that depends on q and the nominator, the joint distribution of these two, and something that depends on q and the annoying, horrible distribution P of x given y that we can't compute. So I have now 3 elements in this, 2 which looks good, the ones in blue, 1 which looks nasty. The last one there is the KL divergence, is the Kullback-Leibler divergence, which is a measure of dissimilarity between 2 distributions. It's always positive, and because it's always positive, it induces a bound. So this thing here, log P of y, is bounded from below by the first 2 blue terms. This is called the evidence lower bound, or the elbow. So it's tight if q of x is equal to P of x given y, because then that term in the end disappears, right? I get log 1. Poof, gone, right? Another way of showing this is that, oh, where did that plot go? Okay, I dropped the plot. Sorry. So what we've effectively done is that we said, I'm going to look for the posterior, I'm going to look for an approximation of that, I'm going to find some parameters that summarizes all the information in y about x, and I can do this by maximizing this lower bound, where all these components are things I should be able to compute. So the things then is here will be the loss function, is written exactly as the previous thing. I have an expectation over q of log p of x comma y, and I have the entropy of q. So this is something that I really should be able to compute. P of x comma y is the joint. If I can't formulate the joint, I don't know what I'm doing, so it doesn't matter. I'm no place to do inference. The log of a distribution, generally we have exponentials, so it's going to be easier than anything else. I'm free to pick q of x however way I want. So I can pick Q of X so that I can compute this thing, and the entropy of a thing should be easy, it should be trivial to compute. So, if we then have this geometrical structure of a composite function, where I have exactly this geometry, can I propose an approximate distribution that reflects the geometry of this parameterization? Well, I can, and the absolute simplest thing is to do exactly this. Super, super easy. So UUT is the eigendecomposition of the general Gauss, the GGN matrix I had before. So what I'm just going to say is that I'm going to have one variance for the kernel. So this is the things where the function does not change, only its parameterization. And I'm going to have another variance in the image, right? Okay? So I just have a Gaussian that has 2 degrees of freedom. And what I can do with this, I now can plug this in to this objective that I had, and I can compute this. Now, the way we compute this is through a method called stochastic projections. So it's a very simple method to do this. First, I draw from a Gaussian. I draw a sample from a big Gaussian. I project that down onto the kernel, first step. The image space is orthogonal to the kernel, so I can get the image part of that sample by taking the full big blob minus the kernel. And then I can formulate the parameter like this. So I just take now the current parameter that I have, theta hat, plus the noise in these directions. And now I've defined a random walk according to this. If I sample through that, I can compute this expectation. So if I do this, here is applying a normal variational bound to this data, the state-of-the-art Bayesian neural network inference scheme called IVON. You can see it just put the same variance everywhere. It's pretty much exactly the same everywhere. The reason for that is that it doesn't reflect the geometry. So these things here have just collapsed. They don't even exist in the parameterization. And if you look at the samples that comes out of this, they look quite nice. Potentially it's something that I would want. So, they look very similar to the diffusion process that I had before, though. The cool thing with this is that this allows me to run models at the scale when neural networks actually is. The biggest models we ran had 22 million parameters, which is kind of cool. You have 22 million parameters and full Bayesian inference. That's something that I'm very excited about. So, I'm going to summarize this talk. Symmetries are really great for learning in deterministic models. I don't like to call deterministic things models. For me, a model is a statistical model. But neural networks, symmetries are awesome. They open up these massive basins of attractions so the gradient descent works. However, they get very problematic for statistical models, simply because we effectively have the same object with different densities. And this is clearly problematic. So, if you then under-parameterize your approximate posterior, so if you had a true posterior, none of this is a problem. If you don't, if you have some form of approximate posterior that doesn't reflect, that can't parameterize all the symmetries, you get these really pathological measures. The Laplace approximation severely underfits because it doesn't reflect the reparameterization of functions. The linearized does this infinitesimally, and that's why it works. So we have an explanation why the Laplace approximation actually works. The covariance of the linearized Laplace defines a Riemannian metric on the manifold of effective parameters. That means we can do all sorts of things. We can do random walks, we can apply new types of variational bounds, and so forth. Now, then comes the potentially cool thing. The factorization tells us what degrees of freedom are connected to the data and to the prior. This means I can think about what parameterization are actually useful for algorithms. I can also do an active learning scenario, right? So say if I've seen a set of data points, right? Now I want to reduce, I want to see a new data point, that disambiguates me as quickly as possible. I have a measure for this now, right? That's the volume of the kernel, right? If I decrease the volume of this, if I get a data point that decreases the volume as quick as possible, that data point is the most informative thing I can have. So that's very cool. So you can do active learning in that setting. I've shown that we can formulate a approximate distribution that reflects the geometry of this parameterization and why that works. And this effectively leads to a factorization of measures. The way we implement this, I'm not storing a 22 million squared matrix of derivatives and computing inverses of them. So everything of this is done using matrix-free algebra. So there's a law, most of the work on this is on the actual algebra. So now I want to come back to the last bit. This is my last slide. So everything I've done have been using this prior. This prior makes absolutely no sense whatsoever, right? The whole notion of being Bayesian about the world, the way I think about it, is that Bayesian inference is the computational form of the scientific principle. It's hypothesis testing. You start with a hypothesis, prior. You do inference on the data that you currently have. You project with your posterior. You see if it fits that, which gives you support or not, right? Bayes' rule is just the computational form of the scientific principle. However, what happens with the scientific principle if you don't know what your hypothesis is? It means nothing. Absolutely, utterly nothing. So, all these uncertainties I showed you mean nothing. They're fluff that came out of me setting that to some value. But I have no idea what that means, right? It's an isotropic distribution over some weights. I have no idea. 20 million of them, right? I have absolutely no idea. So therefore, and this is a hint to my talk tomorrow, I think parametric models makes absolutely no sense when they're this big. There's a fallacy of us learning how to interpret things that have 3, 4, 5 dimensions, and we think, oh, they make sense. Therefore, they make sense, 20 million of them. They don't. And because that, our priors don't make sense. And therefore, our posteriors, neither our predictions make sense. So this work has really been about trying to understand things, not building models that will be useful. I'm not going to use these models for anything in anger at all. Right? But I'm really happy about trying to understand them. So with that, I'm going to finish this talk. So thank you very much.
Bueno, tenemos tiempo para un par de preguntas. ¿Alguien quiere intervenir? Bueno, agradecemos nuevamente a Carl por su gran charla y thank you very much for your talk. Y nos vemos ahora en el acto cultural. Muchas gracias.
So I just want to say one thing in the end then to I know a lot of people here are statisticians. A lot of you work on this bit that I talked about in the beginning, really handcrafting models for specific things. Then all these machine learners, Silicon Valley bros, right, come in with gazillion amounts of computes and show some fancy data that doesn't actually mean something. It's irrelevant, right? All these very, very good statistical models, when you actually apply it to real data, that's where it's at, right? And if there's anything you can do, is to start trying to interpret things like this, right? Maybe we can make sense of them, but at the moment, I'm not putting myself in a car that's run by a neural network. That's one thing that's for sure, right? Or having my doctor making a diagnosis based on it, right? But a statistical model, absolutely, right? Cool.
para cerrar este primer día de nuestro 34º Simposio Internacional de Estadística, tenemos dos momentos finales especiales. El primero es que nuestra universidad quiere ofrecer una pequeña muestra artística con su ballet folclórico al mando del maestro Fabio Martínez. Al finalizar esa pequeña muestra, tendremos un pequeño brindis también, pero como en este sitio especial no podemos tomar bebidas alcohólicas, debemos desplazarnos al segundo piso de la Biblioteca Alberto Quijano, que se encuentra, ustedes salen y a mano derecha se ve el edificio. Entonces todos debemos irnos al segundo piso. Muchas gracias. Entonces con ustedes la muestra folclórica de nuestro ballet. Muchas gracias. Diego, ayúdame a tirar las... ¿Dijeron?
acá. Bueno, bailar y hablar no es fácil, pero tampoco es difícil. Bienvenidos a la Universidad de Nariño, este espacio cultural que desde Bienestar Universitario, la Coordinación de Cultura y nosotros, como ballet folclórico, les regalamos para que se lleven un pedacito de nuestra memoria. La inigualable guaneña, la primera interpretación de los chicos, baile por excelencia en nuestro departamento. Un bambuco insignia de todos los nariñenses y de todos los pastusos. Y este personaje extraído de la fiesta andina, ese carnaval y esa fiesta que los primeros días del año le dicen bienvenidos a todos para vivir la fiesta en unidad, al lado de nuestro majestuoso volcán Galeras, el Urcunina, el polvo, la carioca, la espuma y la pintica son parte de esa memoria de nuestro territorio. A ustedes, muchas gracias y hasta una próxima oportunidad.
Lo dicho, a nuestro brindis.